Okay. So first, thanks everyone for the opportunity to explain what Riverlane does and what we are trying to do in the near future and in the long term. The first thing I start with a quick outline, so you can see how I'm progressing through the presentation and you don't get bored, hopefully. The premise I want to make is that I'm, as Ali was saying, my background is in engineering, and we are a software company with quite a significant proportion of people working on quantum research and applied quantum research. So I picked their brain in the more quantum portion of this presentation. If I'm not happy to answer any question at the end, I will use either my team or the research team to get back to you with a proper answer. So apologies if I'm relatively new to quantum computers, so I hope I'll do my best, but there might be something that needs some extra investigation. So let me start with assuming I think the first important question is why people should care about quantum computers in general and why we should invest time on them. And I think, at least to me, this was like an interesting representation that says that we, from a computational perspective, we see already that there is a subset of NP problems, so non-polynomial space and time execution problems that can be tackled via quantum computers. Some of them can be converted to polynomial execution. Some of them will remain NP, but the complexity will be significantly reduced. This is important because obviously we need to motivate the cost of quantum machines and learning new things and the complexity of the interfacing them, and they shouldn't be just giving us a by 20% improvement. So people are looking at by 10, by 5, by 100, by 1,000 improvement. Something that I recently found out, as I was saying, I'm not quantum computational specialist. There has been discovered a class of problems that is actually that can be treated with classical resources, but can be that is solvable on quantum machines. From Riverlane perspective, what we care about, and I will explain it better later, is mainly addressing the problem of simulation of quantum systems, or simulating the quantistic nature of interactions and for materials, drugs, discovery, and chemistry in general. There is a nice quote from Feynman that says, yeah, we need a quantum machine to simulate quantum systems, and we, in the community, we all believe so. So again, assuming, trying to start from the bottom, it's important to point out that you will get quite a lot of, at least from the news, quite a lot of vibe and news about massive speedups that quantum machines can produce. So you think of Shor, you think of the quantum supremacy experiment, you think of Grover in a sense, but in reality, these applications have even though they have a significant impact in our society, they are not as spread as other computations that can benefit from quantum machines. So at the bottom of this pyramid, you will see that there are more BQE, QPE, QoA, that are ways to accelerate more classical simulations and processing that are at the base of all, again, drug discovery, material discovery, chemistry, interactions analysis, and even if quantum machines will provide a lower speed up than for Shore or Grover, they do provide a speed up that motivates the usage of quantum machines. So where do we stand now? So at the moment we are in the yellow area. So today we are at Riverlane. We are working with potentially all the quantum hardwares on the planet or close to that, or we are in talks with them. And the situation is that most of the companies are in the tens of qubits. Some companies are reaching the 100 of qubits. And what does it mean is, in terms of computability and capabilities of this system, is they are excellent proof of concept, but they are a bit short in terms of qubits to actually deliver any commercial result. There was a lovely quote from John Martinez, the ex-Google, the designer of the Sycamore qubit, that today this yellow area was about proving that there is no, the physics doesn't change when you move from 10 to 20 to 50 qubits. So nothing crazy happens. So now is about moving from the orange yellow portion to the green and blue one. Is about a large number of engineering challenges, but the physics is well understood, and the problem is approachable. So moving, as I was saying, to this dark green region, we start to have 1,000 qubits, and this is where Riverlane is specializing at the moment. We see that there is a lot of potential for starting chemical, pharmaceutical, and physics simulation with this number of qubits. These simulations will be potentially not yet commercially valuable, but they will provide valid results, and they will set the pace and the software and everything for the blue phase, in which you start to have 10,000, 100,000, 1 million qubits, and what's called the fault-tolerant era. So at that stage, we have enough qubits, and I will explain in a bit what I mean with enough, to consider them on pair with classical machines in terms of quality of the results. Plus, they will provide the quantum advantage or the quantum acceleration that they've been designed for. Now, yeah, this is the reality check I want to do here. That is, probably every time if you go on technical papers, is normally people talk about physical qubits versus logical qubits, but when it's a PR kind of message, you normally only see the number with no identification whatsoever what we are talking about. So a physical qubit is the low-level qubit, is some technology that implements one quantum state that can be modified in different ways, but that allows you to do entanglement, quantum operations, and then measurement. The problem with these systems is they are real systems, and they are quantistic by nature, and they need extremely complex boundary conditions to operate. So they are still characterized by quite a significant amount of error. What we see, what is publicly available, is that companies have about 10 to the minus 3, 10 to the minus 4 error rates. And if you think about like a traditional memory or a traditional classical logic component, you talk more likely about 10 to the minus 15, 10 to the minus 12. So this means that if you run for a long enough sequence, and you need to run a long enough sequence to do some valuable computation, you won't get the right result. To compensate for that, there is a concept of logical qubits. So you group, in general, you group physical qubits, and you apply error correction to those. Quantum error correction, so it's a specific implementation of, well, is a different way to error correct than classical, with classical logic. And what it gives you is it gives you the error rate that we are more familiar with coming from classical. So at that point, you can start think of a quantum machine as something that you see in as a computational as a quantum computational designer or application developer as a perfect machine. Now, where Riverlane stands? So one of the things we're working on is trying to. Our team is initially was 50% research and 50% engineering. Now we are a bit more on engineering, but we still have a strong core of chemistry and drug discovery. And we think that we are almost ready in terms of quantum hardware to produce hybrid applications in which we drive, let's say, 99.9% of our simulation of the molecule via classical methods, and we have a 1% or 0.5% or 0.05% that is simulated on a quantum machine. The advantage of that is that that 0.5% is normally the area in which you want to focus and get improve on the chemical accuracy. You want to see exactly the ground state. You want to see all the aspects of the atoms, the atomic interactions. And to do that properly, you need a quantum. Either you need a exponential amount of time, or you need a quantum machine. So this is where we think one of the initial benefits of quantum machines lies. And the interesting thing is, obviously, if you work with this sort of Matryoshka, Russian doll system, you can expand the number of qubits you're using for the quantum part and get to better or faster result. And what we see as an evolution, obviously, at some point, even with a extremely powerful quantum machine, you will not want to simulate everything at the quantistic level, and you will still, and this may lead to save on cost, because running on a quantum machine, you will potentially be charged per shot, per circuit, per minute, and you will still get a benefit from running an hybrid classical plus quantum simulation of your drugs or materials. Now, I think, and I hope everyone will be happy with this. Coming from an engineering background, I will try to explain a bit what we've seen working with at least all the UK labs, all the UK quantum labs, and what we and from an application perspective, what we learn from there. So the first thing is there are many recipes to make qubits, many recipes that uses many ingredients, and the main ingredients are atoms, real atoms, and in this case we see ions and ion traps and cold atoms. Then there are superconducting technologies and semiconducting optical technologies. In this talk, I'll mainly focus on ion traps and superconducting technologies, not because the other two technologies are not promising, but just for for the sake of time, and B, for showing you the ones that have already some commercial interfaces available to the public. So in terms of atoms, ion traps and cold atoms, they operate in vacuum chambers. They don't require special treatment in terms of special conditioning in terms of temperature, and they operate through magnetic fields and lasers. Again, every lab has a different recipe to do that, but that's the general vibe. And one of the main technologies relies on getting this ion from an excited state to a ground state, and mapping these two states to Cat1 and Cat0, and using the lasers and other and the magnetic field to entangle those and obtain a quantum system. Superconducting technologies are a bit different. They provide the same result of giving us something that implements in which we can see a Bell sphere and have a cat0 and cat1 and the entanglement and all the basic operators, but they do rely on a completely different set of physics laws. In particular, they operate at ultra superconducting temperatures, so they are in the 10 to 100 millikelvin regime, and they mainly operate through special types of let's call them classical circuits, so Josephson junctions and RF squid, that have at quantum regimes provide they show special quantum behavior. Just sake of interest, semiconducting and optical, they have an excellent potential because in both scenarios they are less picky in terms of environment. They can operate higher temperatures and they in both cases, and they can rely on existing materials / technologies. They are less mature because the research has started a bit later than superconducting and ion traps. Pictures of some of the labs we working with. As you can see, quantum machines are quite big. So everything that has a color is an important part of the system. Now, again, sorry if everyone is already familiar with this, so I'm trying to develop a common language. So I would start saying that a gate set is the set of quantum operations that are performable on a quantum machine. I'll add that there is a concept of native gate set. So there what's called a universal gate set, or there are universal gate sets that are a set of building blocks that, like in standard electronics with the XOR and the NOT let you define everything you want. There is the same in quantum computing. The main difference here is that each lab has a different what's called a native gate set. So they have a different way to support this, and this is because their technology makes something easier to implement. They should all be equivalent in terms of what you of like universality, but obviously they are different. A measurement is an operation that collapses the quantum state, and from a superposition of cat0 and cat1, and you always get either a 0 or 1 with probability that depends on the wave function. A circuit is a sequence of gates, so quantum circuit is a sequence of gates that are executed, and we normally see them executed after a stage that is called preparation and before a stage that is called measurement. So the preparation is normally the state that creates the quantumness in the system, and the measurement is the state that collapses the quantumness into a classical state. Coherence time is an important metric that represents the amount of time that the system will remain in a quantum state with and this is because of thermal noise, because of environment, because of the way that like these systems are designed, and it represents an important metric because it relates to the depth. How many gates you can execute in your circuit. There will be how many steps, given that each step takes time, you will know that you can do this number of gates between an initialization and a measurement. I think the penultimate one is the concept of single and dual gate operators. So in literature, you can have ternary and n-ary gates. in practice, most of the companies implement 1 qubit or 2 qubit gates, and an example is a rotation over the Bell sphere. So you start with a quantum state and you move it on the sphere. The second one is an example is a control knot, is a state that applies or not or doesn't apply an inversion to a quantum state depending on one control bit. It's important to mention those because I will explain later, there are some properties that are not, that might be different in some of them. And the last bit is the fidelity. So the fidelity is the likelihood that your quantum hardware will perform a gate with no error. So, and this can be gate dependent. So you can have a machine in which the rotation is more likely to cause an error than a knot. In some architectures, obviously, because these are real physical systems, you might have crosstalk, and you might have that when you execute on one qubit, the neighbor qubit might be affected by that, and that will cause your error to increase. Now, I should have mentioned this before. This is the Bell sphere. So what you see is you start from a ground state, and then you initialize your system. Normally, you initialize it to get 0, and your operators will move it across the sphere. So keeping the radius to the unitary, and you will and the operators are generating the superposition and the quantumness by moving away from 0 and 1 and staying everywhere else on the sphere. When you perform a measurement, depending on where you are and your probability, you will collapse either to the 0 state, to the 0 state or to the 1 state. And the way that normally these are represented in code and documentation and literature is via matrix operators. These obviously are not considering any error, they are not considering, and they are an abstract theoretical representation. As I was saying, the dimensionality of the matrix is twice the number of qubits that you're driving. So CNOT is a 2 qubit gates with is a 4x4 matrix, and a rotation is a 2x2 matrix. So now let's start to move closer to probably what's of interest. So now if you were to run a pure quantum algorithm, you will not get much of it, as in you can run one simulation, and this part is extremely fast in quantistic sense, but it will be extremely slow to actually run all the classical logic around it. So what is normally done, for example, in this case, is the variational quantum eigensolver. The problem is split into something that is assigned to a classical computer and something that and the part of computation that is fast on the quantum computer. Only that part is executed on the quantum computer. So in this case, what we're trying to solve with the VQE is to calculate an Hamiltonian, pick a phase, and then create a circuit that maps that into a quantum state, measure it, and then try to infer the ground state energy of the system by alternating and tuning on the phase value until the quantum estimate is returning you have reached the minimum of the function, and this is intrinsic to the quantum computation. Now, what does that mean is that I have my classical computer side that is normal code, and when I generate the circuit, depending on the number of depending on my argument to the function, I will get different configurations. So in this case, I'm doing an H2 molecule, so it's already quite large in terms of quantum utilization, and this gets mapped to these sequences, this sequence of rotations. All these Ry and Rz are rotations across the Y and Z axis on the Bell sphere, and combined with this plus that is a C naught. This is actually longer in reality, but you will, if you execute from qubit 0 to qubit 3, initialize them to a special state, a special combination of ket 0 and ket 1s. You execute this circuit, then you will get a solution that should represent, if there are no mistakes, the ground state of your Hamiltonian, given that you provide the right phase to the system. Now, when does it get interesting? So now with so H2 sits kind of on the left of this. So H2 needs about 4 to 5 qubits, if I'm not mistaken, and no one really needs to run it, as it's plenty covered by classical methods. O2, N2, CH4, they are still like, they require 20 to 40 qubits, and they are still not interesting, but they start to look a bit more appealing. And then as we move to more complex and to larger systems, we start to reach the sweet spot in which these simulations will be, if we were to do it in a quantistic way with the targeting the right chemistry accuracy, they will take the age of the universe to be computed. So the moving in the kind of in the infrared of this, we start to see the advantage of quantum computers. And the nice thing is the same algorithm can, obviously it will take a bit longer on both classical and quantum sides, but with the right infrastructure in place, there will be just passing a different molecule and passing a different problem to the same software. So now that's lovely, nice, and great, but that's not what really happens in life, or at least what doesn't happen yet. So a quantum computer is an HPC, or at least is a super heterogeneous system with some with layers and with different properties and duties and capabilities of each layer. So normally each lab, and I think this color scheme is giving is using the right legend. So the orange portion is what you would think as a classical PC. And then there are FPGAs or dedicated hardware units that are still operating in relatively slow domain in terms of signal processing. And then there is a relatively fast or ultra fast portion of logic that is either field programmable gate arrays, so FPGAs, or ASICs, so custom-made chips that needs to operate at nanoseconds regimes. And this is because there is the blue part that is the control of the quantum system, that given this coherence time concept needs to be fast enough to make adjustments and operations within the lifetime of the quantum state. Qubits, as I was saying, on top of being generated in different ways, they have extremely different properties. So I would probably read this diagram from the bottom up. So if you're working with ions, you normally have 100 microseconds, milliseconds of coherence time. Some experiments, they go up to seconds. Superconducting, they have much shorter coherence time, and we are talking about 10 to 100 microseconds. And silicon has potentially an extremely long coherence time when some limitations will be overcome. The other aspects of the different technologies there, the gate time is different. So from these numbers are the gate times, the one at the bottom. So to execute one gate on ions takes about 2 to 3 order of magnitudes more time than on a superconducting qubit, in particular if we want to measure or initialize the system. Now, why that happens is because the technologies are completely different in terms of the way we drive the qubits. So I picked two. I picked the superconducting and ion trap. For the superconducting, that's a Sycamore chip. At least one slide from the Santa Barbara University of California Santa Barbara group, and it's quite interesting. So it's just is using special properties of superconducting materials. And I will, from my engineering perspective, I will simplifying, saying that the low temperature allows for better control of the electrons, and with a better control, we can have the interactions that make the system that allows us to play with the excitement of the electrons, and we can use RF signals at 4.8, let's say 5 gigahertz to change the state of the qubits and perform all the operation, or at least a set of the gates, quantum gates that are needed to implement a quantum machine. It is a really challenging problem to design this kind of chip, because we are operating at a temperature that is which any emission, noise, any thermal dissipation needs to be accounted for and compensated. And they are, this is the way Google is scaling up, and other companies are scaling up to 100 or 1,000 of qubits soon. And one thing that is important is that they have a connectivity. So they, if you see the small diagram on the block, a qubit that is the X, the cross, can only talk to 4 neighbors. I will explain later why this is important, but this implies that when you write your algorithm, something has to take care of that and know how to map this circuit to the right location of the qubits. Ion traps are different. I put together different ideas just to be generic and not confidential. So ions, they are real quantum systems. They're atoms, and what we do in this case is they are confined in traps, at least in ion traps, and they are excited in different ways via RF magnetic fields and lasers. And the important points are that they can be moved around. So you can have your grid of ions and move them as you need. And they can be measured normally via lasers plus CCD, so plus cameras, or via PMT sensors. An interesting bit here is that they have a full connectivity because of this shuttling that allows them to be moved wherever you need them. And they are more easy to scale up in terms of creating a deck of like interconnected smaller units. Their coherence time is much longer, and again, the quantum state is achieved by playing with the excited ground state of the system or the hyperplane state. In this case, they operate in vacuum, and generalizing, moving away from the hardware one step and reaching what we call the circle level. And what you do now is you pick a language. There are probably 10 at least I can name that describe the quantum computation part. I pick OpenQASM, that is from IBM as open initiative. And what you do, you define your gates and your registers. And then you, in this case, these 8 lines, you perform another mark gate, and then you do a CX gate on Q1 and Q0, and you measure them. And this is, I think this is not, yeah, it doesn't represent the same picture, but the idea is that you get this code converted into your native gate set. So in the building blocks that your machine supports, there is something that is scheduling that normally on the CPU level. They get pushed down to the FPGA that is, or the FPGAs that then are controlling all the generation of the electrical fields, the magnetic fields, and everything that is maintaining the system in a quantum state and is applying the operators. And this is the applying the low-level control. So the sequence the sequences come from the FPGA or the ASIC, and they are almost all the technologies that rely on sending, on shaping high-frequency signals, and these high-frequency signals, they resonate in a way or another with the energy levels of the atoms, of the electrons, or anything in the system, of the quantum part, and they allow us to change its state. There are lots of technical interesting points here. I just mentioned one that was shocking to me, that because you're operating at this, for example, at this millikelvin, in this millikelvin regime, quite a lot of things that we give for granted in terms of electronics and electrical wiring and signals are to be thrown away, and there is like quite a lot of extra complexity. Now, to materialize it in a better view, this is again pre-Sycamore, so again Google. This was from the University of Santa Barbara, and this is the way that we actually generate, we control the qubits. So the 0 to 4 crosses are what you see on the image, and what they do is, on the right hand side we have the sequences of like pulses that you have to generate to perform all the operations. So in this case, you see the time scale is about 300 nanoseconds, and lots of things have to happen in 300 nanoseconds to do simple things with this qubit. I think this diagram is just doing a few basic rotation and few basic operations on all of the qubits. And yeah, and this is up to today, and it covers completely the physical qubits. The interesting bit is what I mentioned at the beginning, the logical qubits. So there is a lot of research going on error correction, and the important message to remember is that it is totally doable when we reach a fidelity of 10 to the minus 4. So if our physical qubit is stable enough to deliver a 10 to the minus 4 error rate, we can build on top of that and create logical qubits. The complexity comes now from implementing this thing in nanoseconds or microseconds, because like on this image on the right represents a surface code that is one of the ways to encode the extra redundancy needed for error correction. And the qubits are the gray blocks, and the white blobs are instead, they're still qubits, but they're not used in any computation. They're just there to help us correct the errors. And the way they are solved is quite complex. It requires computations that are not needed in any way or shape in traditional, in classical computing. This is an example of union find decoder that is a way to identify errors in this in a quantum system with basically no memory and quantum properties. Now, this is where Riverlane comes into place. How do we want to improve? What we are doing to improve the existing solution. So as I was saying, there are few limitations, at least as far as we can tell. Every vendor is coming up with something unique. So if you're an application developer, even if you have to integrate applications, you will have a plethora of libraries, a plethora of completely different implementations. So one thing we're working on is to try to provide a standardization effort in that direction. There is another improvement that is important, that we want to. Other companies are, except for the big four, are kind of startup level, and we believe they all have potential to do something great. So as a software company, we want to help them kind of reach their next goal, and we need to do that. We need to show that they can deliver. They are close to deliver something that has commercial value. And the other point is, this is more close to my heart, is that we have loads of expensive equipment. So you probably have 500,000 of electronics just sitting around to implement your quantum system, and you may not be using it the optimal way in general, and that will give you like maybe not the best possible outcome, and will limit the amount of computation that you can do or the quality of it. So what we call write once, run many. We're working with all the startups, all the quantum startups in the UK, in this Innovate UK bid. We started last year, and we're trying to standardize, and we're working with MPL as well. We're trying to standardize the way you talk to a quantum machine. And we call it the hardware abstraction layer. So we can say is a way that every language that every hardware should understand. And why we want to do that is to help the developers. So even if you don't write an application, you benefit from having to a more verified code. So helping the application and the application users and the integrator. And the way we're doing it is we have this collaboration that is going on with these 6 partners, and we are testing this integration on their system at different level, collecting feedback and understanding what they need. Given that there are 34 commercial startup labs on the planet, we're working with 6, so I think we're getting a good vibe for what's needed. And what we are finding is that there is an appetite for application developers to gain access to more systems and being able to not to start again every time with recoding completely because they need a new language. So we're trying to bridge the gap there and make something that is hardware agnostic or hardware optimal, but hardware independent. On squeezing the qubits, one of the things we are trying to do is we are trying to identify ways to squeeze computational power out of qubits, and to do that we are working at trying to bring, as I was saying, the right level of control where we need it. So at the moment you write your code and it's sitting high up in the stack, so you basically have no access to the low-level electronics, middle-level electronics, and CPU. We are changing this with our Delta language, our product that is open source, and is trying to convince everyone that we can use at best, or we can give them a way to use at best the resources. This is important because there are ways, alpha VQE and all of VQE, that are to use existing hardware, quantum hardware, or relatively near in the future quantum hardwares, and do something already interesting. And to do that, they need a better integration in terms of hardware. The way we do it, simplifying a bit, is we say, well, normally you will write, as I was saying, at this level, in the green box. Our language lets you write at potentially any level except for the blue one, because it's normally not programmable, but gives you 2 extra points of entry, 2 extra points of optimization for your code. And we are trying this work is intertwined with the hardware abstraction layer proposal. So we're trying to get everyone to understand the benefit of having this, what we call local control. So this capability of making the decision at the right time in the right point, instead of always having the decision I in the green block at the top. So again, why we think this is important? I think if you use the existing paradigm, for most of the technologies, every time you want to make a decision based on your circuit, you have to throw away about 1,000 execution that you could have done. And by moving down this control, you can reach the point in which you can basically pipeline everything. And when you make a measurement, you can make a decision from the circuit and make something like VQE or alpha VQE or hollow VQE much faster and much more better value for money. This is one study we have done in the past. So we show that by using either Deltaflow or our computational model, you can accelerate. This is obviously the best case scenario in which we are just measuring one real fast loop, but we see benefits in the order of by 10 just by having this, by pushing the control down to when it's important to make the decision in a quick way. Obviously, what we're trying to do is we understood that there was a problem. We came up with this framework, Deltaflow, that provides like language, tooling, etc., to define this connectivity and to allow you to write code in to simulate a full system like this, so an FPGA, multiple FPGAs plus multiple CPUs on your machine, and to provide a language that is similar for all the blocks. So you don't have to learn yet another language. You can use the same Python framework for doing both. Yeah, I think this is one thing we are going around the labs doing is a Rabi oscillation. That is a real simple example. And what we're showing them is that we can do this low latency implementation of a really trivial physical experiment without them changing most of their existing control stack. And we can do it in a way that shows the benefit of having this decision made at the lowest level possible in your system. And this will greatly benefit the uptime of the quantum machines as well, and this will benefit what you can run in 5 years' time, and etc. So we do believe and enable something that we call the quantum control level 2 or version 2, in which we try to democratize the control of the quantum hardware. If you have like a system like Sycamore or other, there are potentially 100 FPGAs and potentially even 20 plus CPUs. Each of them needs to communicate and talk, and having you want to have sort of a peer-to-peer system more than a hierarchical system to make your life easier. And our language is designed to drive you in that direction. And this is obviously for hardware labs and for application developers. Now, and this is the final set of slides, or yeah, might be a bit long. Messages I want to convey. The quantum hardware is really accelerating now in terms of development, and the labs are moving in quickly, improving the quality of the qubits and improving the size of their system. This interfacing is a bit unclear, but we are working with the labs on that and the community later. And from a kind of HPC perspective, we have to put like start, and we started with this hardware abstraction layer committee, thinking about latency and thinking about the interaction between a more traditional HPC with the quantum machine. So is it okay to have the quantum machine sitting in the cloud, and the latency will be tolerable, acceptable, or do we want to have load the quantum machine lab with extra GPU, TPUs, APUs to provide to allow extra computation that is not quantum there. We need, as I was saying, we need to do, the quantum needs to show really big speed up to make it appealing, because it's not going to be cheap for the near time. And as I was saying, we think that local control is an important aspect that needs to happen to make the best out of this technology. Yeah, I will just share the possible roadmap that we think is already happening. That is, we make the best out of NISQ, so this noisy area, and we understand, we keep the hardware labs developing great solutions. We don't have just one player or two players. We integrate this, we start these hybrid solutions with classical and quantum system. We come to a conclusion with the cloud model in terms of security, performance, and then we increase this the quota of quantum in the hybrid systems, and at that point we start developing libraries like quantum ready, and then we do quantum verification, and finally we can pull like companies in and run something that is valuable for them. And then at that point we just like enjoy the ride, just do something that comes from Google. So this is the kind of ride that you could get if everything goes, if you're running something that is that from NP moves to P, so age of the universe versus 24 minutes. So this should be it for me. Sorry, I've been super long. Sorry.
Okay, thank you, Marco.